Learning to scuba dive, like I did in the second voyage of the Mimi, can teach you a lot about pressure and what it does to you. But it did make me wonder about some things, so I came here to try to get a few answers. This is the North American Hyperbaric Center on City Island in New York City. Hyperbaric means high pressure. The people who work here should know all about it. At least I hope they do.
The reason I hope they do is because today they've promised to put me into one of their high-pressure chambers. But first I get a lesson on just what pressure is all about.
Glenn Butler?
Yeah.
Ben Affleck.
Glenn Butler is one of the diving experts at the center. He started out by showing me a small hyperbaric chamber.
We can pressurize this to a depth equivalent to 10 atmospheres, 10 times atmospheric pressure.
10 atmospheres of pressure. How do you get that much?
Well, we have air cylinders outside that push air into this chamber. And because the volume is fixed, as we push air into the chamber, the pressure goes up.
But by the volume being fixed, I mean, there can never be any more space that the air can take up.
That's right.
So it has to become more dense?
This is a steel chamber, and it doesn't expand like a balloon, okay? So it holds its shape. As a matter of fact, it's over 4 inches thick in spots, okay?
It has to be that thick to hold 10 atmospheres of pressure. Just walking around, we're all under the weight of the atmosphere, about 100 miles of air, producing 14.7 pounds of pressure on each square inch of our bodies. We all know that water is a lot heavier than air. It takes only 33 feet of water to produce the same pressure as 100 miles of air. That pressure, 14.7 pounds per square inch, is called 1 atmosphere of pressure. I brought along a bunch of different things to put into the chamber. I wanted to see what pressure did to them before I found out what it would do to me. We started with a basketball. A basketball is hard because of air pressure inside the ball, about 7 pounds per square inch more than atmospheric pressure. I sure couldn't squeeze it much. It was hard to imagine how just air pressure could.
It needs to be heavy to hold back all the air pressure. Okay, now, we swing this big hinge around here. Swing it shut. This door has to hold back 46 tons.
46 tons?
That's right. That's right. Okay? 130 psi, which is pounds per square inch, at 10 atmospheres, okay, over this whole door area, which is 2.5 feet in diameter, adds up to 46 tons. So why don't we step around over here to the controls?
Over here?
Yes, right around this way.
All right.
Now, this valve here lets air into the chamber, and this gauge shows up to 700 feet seawater.
Okay.
And we're going to work in the first 300 feet or 10
We're going to go 300
atmospheres.
feet?
Sure are.
They measure pressure at the hyperbaric center in feet of seawater, as if they were underwater. That's because it's a dive school. But of course the chambers are actually dry, and the pressure is produced by air.
Make sure everything's shut that should be, and we'll begin to compress.
Can I look in here?
Sure can. Okay, we're at 10 feet then, 10 feet of seawater. And compressing.
Whoa! Look at that! All of a
20
sudden,
feet.
just caved in.
We're at 20 feet now. 30 feet. 33 feet. We're now at 2 atmospheres pressure inside. That's twice normal atmospheric pressure. And the volume of the ball is roughly 1/2 its original volume. 60 feet.
Yeah.
66 feet. We're now at 3 atmospheres. We're now at 3 times normal atmospheric pressure.
At 3 atmospheres, or triple the atmospheric pressure, the ball contains 1/3 the volume of air. At 4 atmospheres, 1/4, and so on.
165 feet now. That's 6 atmospheres, 6 times normal atmospheric pressure.
We haven't let the air out of the ball, right? I mean, there's still the same amount of air in there. Is that right?
Yes, the same amount of air is in there, but we've squeezed it. We're using outside pressure on the ball. We've squeezed the air on the inside of the ball much smaller. Okay, well, we're at 10 atmospheres right now, 10 times normal atmospheric pressure, and the volume of gas inside is actually almost 1/10 the original volume.
That really is flat.
Okay, shall
Okay, you ready
shall we depressurize it?
Yeah, let's see it come inflate right back up.
All right, keep an eye on it. Now we're going to go from 10 back to the surface now. We're letting air now out of the chamber. 160 feet. Just passing 66 feet. That's 3 atmospheres, 3 times normal atmospheric pressure.
Okay, now it's halfway filled. Now it's halfway filled.
Right.
So now it should come
33 feet. Now the volume inside the basketball is going to double now between 33 feet and the surface.
I wish I could blow this up every time like this. But I guess it's not really being blown up, right?
No, we're just
it's the same amount of air.
Bringing the forces back in balance so that what pressure should be inside that balloon when the basketball when it's back at sea
7
level.
pounds, right?
About 7 psi.
There it is.
When we took the basketball out, back into 1 atmosphere, or 14.7 pounds per square inch pressure, it was right back to normal.
Now, when it was in there, it was exposed to how much you couldn't squeeze that down like that, could you?
No.
Neither can I. About 130 pounds pressure at 300 feet seawater.
130 pounds per square inch?
130 pounds for each square inch.
If you were in there at 130 pounds, wouldn't you feel like all this pressure on you, or?
Well, that's one of the great differences between gas and liquids. Liquids are incompressible.
You mean you can't press them down?
You're a liquid.
Well, mostly, right?
You're mostly liquid, except for the air spaces like in your lungs and your ears. And you'll learn about that a little bit later from Dr. Sanchez. Right? But your body basically is a fluid, and it's not compressible. So that's how people can go underwater.
Get compressed. If you went in there, you would, I wouldn't become like this basketball.
No.
I'd stay because I'm mostly fluid.
That's right.
Have you ever tried putting any fluid in there?
Yes. Matter of fact, let's do an experiment now where we compare water and gas. Okay?
All right.
All right. Let's get a couple of balloons and fill one of them with water.
All right.
We filled one balloon with water and the other with air. They were just about the same size at 1 atmosphere of pressure.
All right, now, the blue one has the water in it, right? And so that shouldn't shrink, and the yellow one's got the air.
That's correct. 10 feet. Coming up on 33 feet, 2 atmospheres. Coming up on 99 feet. Can you see the little air bubble at the top of the water-filled balloon?
Yeah. Should that be shrinking?
It's shrinking.
At a really low depth, it would look like it had no air bubbles, right?
It'll disappear. It'll actually be absorbed into the water.
Oh, really?
It'll dissolve in the water.
Gases can be absorbed in liquids, and the more pressure is applied, the more gas is absorbed. That's how nitrogen gets in a diver's blood, sometimes causing the bends.
That's how soda is carbonated.
They take it down, they pressurize it, and it becomes...
By pushing gas, carbon dioxide usually, into the liquid. We're approaching 165 feet, and that's 6 atmospheres.
Is the pressure inside that balloon, the water in the water balloon, the same as the air pressure?
Yes, but the blue balloon is not compressible. The water inside it is not compressible.
But it still is at the pressure of the air.
They're both at equal pressures.
Okay. Is that the same with our body? It's not compressed, but it's still, like inside my body, it's that pressure?
That's right. At any given depth in the ocean, scuba diving, the water pressure is exerted all over your body and is transmitted through your body. Okay, well, we're at 230 feet now.
You want to stop and take it back?
Yeah, let's stop and take it back and try something else.
When the pressure on the balloons was released, the one filled with air came right back to its original size, doubling in the last 33 feet.
There we are, just about at the surface.
I was reassured by the water balloon. It looked like my body, being mostly water, would survive the hyperbaric chamber. But the next experiments had me worried again.
Okay, begin compression.
2 light bulbs, an egg, and a gas can. The gas can developed a leak, so it never completely collapsed. And until we reached 300 feet of seawater, or over 130 pounds of pressure per square inch on the objects, it didn't look like anything much was going to happen.
Whoa! Whoa! That was pretty... Oh, wow.
It sure goes off with a bang, doesn't it?
Yeah. It exploded.
It imploded. It didn't explode.
What do you mean it imploded?
Imploded. The gas pressure on the outside was great enough that it actually collapsed or imploded.
Glenn explained why the egg and the other bulbs survived the pressure. First of all, a raw egg is filled with liquid. Plus, gases like air can actually pass through the shell, which is one reason a chick can live in there. It also has a shape that can withstand a lot of pressure. The best shape for that is a perfect sphere.
This is more close to a sphere, and it's another reason why it's so strong, is that now the force is divided equally over it, and it compresses it. And glass on compression is very strong. So that's why this stayed in shape. And the other one broke because back at the shank, which was exaggerated, it had a long area that was flat, and that was a place that could get pushed on.
Next, we tried another can, one we hoped wouldn't leak, and a rigid plastic container.
Maybe you didn't get a good seal on that plastic. It's not really crushing. Whoa!
Well, the plastic is more rigid than the steel, believe it or not, in the can.
Whoa, it's doing flips in it.
Watch real close now.
Yeah, I'm watching.
Now I was beginning to worry again about going into the big hyperbaric chamber, and our last experiment didn't make me feel any better.
I think you're just about ready to go under pressure yourself, so let's see what might happen to your head, all right? We'll put one inside and we'll keep one outside for comparison, all right?
All right.
I think Glenn was just having fun with me. The styrofoam head is made up of thousands of little plastic bubbles filled with air.
Should I close it up?
Yeah. Start compression.
Okay. You think this is going to happen to my head?
Well, let your head fill with styrofoam, which is the possibility.
It's disgusting.
Far
Looks like
more.
something from a horror movie.
It does. It does. It looks like science fiction.
In the back, it looks like his head's going to pop or something. Ooh, that's really gross.
270 feet. We're almost at 300.
Some of the tiny air bubbles in the styrofoam must have burst because the head never did come back to its normal size, even after we took all the pressure off.
I hope that doesn't happen to my head going under there. But I guess it won't, because my head's not made of air bubbles, hopefully.
Now it's my turn to get squashed. I know it won't hurt me, but I'll be under the pressure of a 100-foot dive, 4 atmospheres of pressure, and I just can't forget that head.